Hello everyone, welcome to our Chapter 6 video tutorials. Chapter 6 deals with functions, which is a concept that I suspect is very familiar to most of us. And so this chapter will function mostly as review, primarily aimed at refamiliarizing ourselves with the core properties that functions can have, because we're going to want to combine our knowledge of functions with our study of groups. Pretty much every mathematical object is studied by looking at its internal properties, its basic properties in itself, and then comparing how those properties interact with special kinds of functions. And so in order to do that for groups, we're going to start by reminding ourselves of how functions work just broadly. So for us, a function, we have two kind of blobby shapes, and then this blobby on the left represents the domain. And a function is an assignment of inputs to outputs. The outputs are called the codomain. The collection of values that are actually achieved is called the range. The range doesn't have to be everything. There could be things not in the image of this function, like these guys over here. And the function is the whole package. So that part is sometimes overlooked, that the function is all three of the domain, the codomain, and the actual mapping properties itself. And with this core idea in mind, we're going to isolate basically two special properties, well, three if you put them together, special properties of functions in this lesson. And so without any further ado, we have the first of these, which is what we call injective. This is also known as one-to-one. And let's give a precise definition. A function f, x to y, just two sets, is called injective if, given two different points, they go to two different places. Sometimes you see this reworded, if we remember our logic, with the contrapositive, where we negate the conclusion of the statement, reverse the implication, and negate the premise. This is sometimes helpful for proofs. F of x equals f of y implies x equals y. Because generally speaking, when you want to prove something, it's easier to prove usually a statement involving equalities than a statement involving inequalities. And so one can try to use maybe algebra methods to rework the whatever the function is and try to undo it step by step to achieve x equals y. So that's one proof strategy. Maybe I should show like an example of this. How about we look at x cubed plus 1 for a simple function. F of x equals x cubed plus 1. This is an injective function. And actually, I'll show two proofs of this, because one of them directly from the definition, and then I'll show another one that reminds us of some calculus facts, often just very helpful when dealing with functions in general. So why not? If f of x equals f of y, then we have x cubed plus 1 equals y cubed plus 1. We can subtract 1 from both and get x cubed equals y cubed. And then we have to remember something about cube roots. With real numbers, every number has one cube root. Unlike, for example, with square root, where there could be positive or negative. because, well, 1 to the third power is 1, minus 1 to the third power is minus 1. This implies x equals y by taking the third root of both sides. Another common way of proving things involving real functions is to use calculus. So, for example, we can see by calculating the derivative of this function that this is always positive, and in fact, it's only 0 at one point. That means that this function is increasing. And what do we know about increasing functions? Well, essentially, writing out the definition, we say that if x is bigger than y, then f of x is bigger than f of y. And so, of course, if x is merely not equal to y, implies one of either x is more than y or y is more than x. And in either case, these are also not equal. So in other words, a function which is increasing is always injective. This is just one of those things that's just super helpful to just know. Okay, let's continue. Let's look at surjective, the other common property. Surjective is often called onto. And again, let's give a precise definition. Function is called surjective if for every y in y, there is some x in x such that f of x equals y. In other words, if we scroll all the way back up to the top, what we're saying is this kind of thing never happens. Everything in the codomain is actually hit by something in the domain. I think for this kind of problem, there is not as general a method that I can think of off the top of my head. For example, using calculus to check that something is surjective. We kind of just have to do it using whatever the task, whatever information we have about the function. Um, Actually, one instance of using calculus that I can think of is the intermediate value theorem. So for polynomials, we have, okay, let's not get ahead of ourselves. The intermediate value theorem says if A and B are in the image of F, in other words, they are two values that are achieved and they're different, then every value in the middle, sorry, I didn't say an important fact. Or in the image of F, which is assumed to be continuous. It's not true if I don't include all the words, right? Then every value in between A and B, every value, how about we call it C, also has C in the image of F. And so, in other words, the picture is something like, you have some squiggle, and then you have like a value here. Here's A, and then we have a value up here, B. And then the point is, no matter what kind of C you pick in the middle, it's achieved somewhere. And so how is this useful for us? Well, for polynomials of odd degree, always have different end behaviors. What does that mean? It means that, for example, if you have an odd degree polynomial, such as the one we looked at before, then the limit as x to infinity is positive infinity, but the limit as you go to negative infinity is negative infinity. It could be the other way around if there was a negative coefficient in front of these guys, but this is positive, and so when I plug in essentially a big number, you pretend it's like a billion or something. This is some even huger positive number going to infinity. If you plug in some huge negative number, similarly, some huge negative number comes out, even huger. And so as such, by applying the intermediate value theorem, I can see that it has to be surjective. Because if I want to prove that any given number, like say 100, is in the range, I just find some big enough positive number so that x cubed plus 1 becomes more than 100. And then I find some other number, maybe I'll call this one x0. I find some other number, x1, with x cubed plus 1, maybe just negative, right? Just plug in a negative number. And then since every polynomial is continuous, you just apply the theorem. And then you agree that I just made up the number 100. It doesn't actually have any significance. This works for every number. And so this uses calculus to prove that all polynomials of odd degree are surjective. All right. And the last important property on our list for today is what we get when we combine these things. We call this bijective. This is injective and surjective at the same time. And so these functions are very special because a bijective function has the property that every value is in the range, and also different points always go to different places. So in other words, a bijective function is basically a perfect one-to-one matching between the domain and the codomain. That's kind of an intuition. It's not really mathematically precise. Maybe if I write the word entire codomain, that makes it a little bit more precise because one-to-one is injective and the entire codomain is what it means to be surjective. Sorry about that. Okay, so I think the only thing left to do is to remind us of some crucial properties about composing functions, right? If we have two functions, f x to y and g y to z, then we can form the composite g circle f. Usually you read this as the word following. This makes it a little bit more understandable why functions are composed right to left instead of left to right. This is g following f. So in other words, first do f and then do g. This is going to be a function x to z directly, right? Because f maps to y, and the g kind of picks up where f left off and sends it over to z. And we have some simple mapping properties for injective and surjective functions. If I have two functions, which are both either injective or surjective, then so is, g circle f. Respectively, assuming, of course, that makes sense. The domain of g equals the codomain of f, right? Otherwise, it doesn't make any sense to say what I'm saying in the first place. So let's just prove these really quickly. And then I think we might be basically done with this chapter. So let's see, how does this go? for injective, we have, again, let's look at the contrapositive version. G circle F of X equals G circle F of Y. We need to show that this implies X equals Y. And here's how we do this. First, we unravel this definition so that this is G of X, sorry, G of F of X, and this is G of F of Y. Now, since G is injective, this means that G, whenever G has the same outputs, then the inputs are equal. And these F's are the inputs into G. So because G is injective, we can cancel G. That's basically what injective means. Maybe we should write that down as a little bit of a slogan to help us remember. Crucially, when I say it's cancelable, I only mean it's cancelable on the left like this. So we can cancel this. And now we have f of x equals f of y. But we just talked about this, right? It's now we're in exactly the same situation, except we're talking about f. And we assumed that both f and g are cancelable. So again, the same argument tells us that x equals y. This is what we wanted to prove. Okay, now we got surjective. For this, we have f going x to y, g going y to z. So g composed with f goes x to z directly. And we need to show that for every z in big Z, there is x in big X such that g composed with f of little x equals little z. And again, we do this basically in two stages. First up, we have, since G is surjective, okay, hold on. Actually, let's not get ahead of ourselves. Let's again write down what we're dealing with, right? We need to show that G of f of x equals z. Unraveling the composition notation. The crucial bit is that since G is surjective, there is a y in big Y such that G of little y equals little z. The magic then is that f is also surjective, and so there is an x in big X such that f of x equals y. Now we put these together. We take x, f of x equals y, g of y equals z. Combining these, we get g of f of x equals z, or g of f of x equals z, which is what we wanted to prove.